All right, thank you everyone for joining today. This is our webinar on elastomer EMI gasket design. My name is Jared Cohen. I'm the Marketing Communications Manager for Parker Comerics. And we have pre-recorded parts of this webinar for clarity and accuracy, and we'll just wait a few more moments for everyone to join before we get into our housekeeping. Thank you.
So just a little housekeeping before we start. You should be on listen-only mode already, but now is a good time to check to make sure before we get started. You will be able to ask questions during the webinar using the chat feature. Our subject matter experts will answer all of your questions at the end of the webinar. And please be aware that we are not accepting anonymous questions, so if you do ask one, your name will be visible. Should we run out of time for questions or just not get to them all, rest assured we will be happy to follow up with you after the webinar is over. And finally, this webinar will be recorded and automatically will be sent to you after the session. So with that, let's begin. All right, introducing today's speakers, we have Sierra Iden and Ben Noodleman for Parker Comerics. Sierra.
Hello, everyone, and welcome. My name is Sierra Iden. I'm a mechanical engineer, and I've been doing technical sales for Comerics for almost 10 years.
Hi everyone, my name is Ben Noodleman. I'm a market development engineer for Comerics and have been with the team for 3 years.
Okay, to start off today's agenda, we'll introduce ourselves and who Parker Comerics is. And then section 1 will be all about electrically conductive elastomer selection. And then we'll move into overmolded and vulcanized covers. Followed by that, we'll talk about housing and groove design guidelines and corrosion and environmental factors. And at the end, we will finish off with a live question and answer. Comerics Division is part of the Parker-Hannifin Corporation Engineered Materials Group and is a global leader in the development and application of electrically conductive and thermal interface materials. Engineers and designers from every industry, including aviation, telecommunications, life science, defense, commercial and consumer electronics, choose Comerics for its strong product portfolio, utilizing technology built on core competencies in material science and process technology.
Our first section is going to go into some details in selecting the right conductive elastomer for an EMI seal.
Hey, Ben, what does EMI mean?
That's a great question, Sierra. EMI stands for electromagnetic interference and is a pretty common requirement in life science, telecom, general industrial, and a lot of military and aerospace applications for just about any electronics box. To give you all a little bit of a background on what EMI seals are, electrically conductive elastomer seals consist of 2 parts, an elastomer base and a conductive metal filler. Both of these combine to create an environmental seal as well as an EMI shield. The advantage behind them is that they can come in almost an infinite number of design possibilities and performance options.
So, Ben, I see that there's 3 different elastomer binders: silicone, fluorosilicone, and EPDM. You know, I'm working on a ground-based vehicle application right now, and they said something about a super tropical bleach.
Yeah, so as you can see, we do have 3 different binder options here. And for your specific application, especially when it comes to super tropical bleaches or CBRN requirements, EPDM is definitely going to be the best option. Silicone's a pretty common option for most applications, except when it comes to interacting with hydraulic fluids or various fuels. That's where fluorosilicone is going to be the best bet.
So what if I just had a standard salt fog, salt spray requirement? Would I need to use a fluorosilicone or EPDM?
No, a silicone should do pretty well in that application.
Okay. And what about choosing a conductive filler? I mean, there's a lot of options, and my customer is really cheap, so I might want to use the cheapest one. Is that always the correct choice?
Not always. A lot of the different conductive fillers have different requirements and different needs that they meet. For example, some of them, like silver-plated aluminum and nickel-plated aluminum, are going to provide you really high shielding effectiveness, as well as high corrosion resistance on aluminum. At the same time, if you're looking for very low contact resistance, a pure silver filler might be the best option, even though it's on the more expensive side. If you've got an application that doesn't require high shielding and won't be exposed to the environment, a more economical solution might be nickel-plated graphite.
So once we've chosen our filler and our binder system, I guess it's time to choose a gasket profile cross-section. How do you know which one to use? So there's several profiles, some being solid, some being hollow. The solid profiles shown on this slide lend themselves very well for high environmental sealing. For instance, a solid O is very good for environmental sealing. It's a very common profile, but the con is that it requires a groove. You can't stick a solid O on a ledge, it'll fall off. And you can't put PSA on a solid O as well. A solid D is also a good choice. However, when curving around a corner or trying to slice into a ring, it could have a tendency to roll over on itself.
Sierra, what about these profiles? They all look like they serve a slightly different purpose.
So yeah, the typical hollow profiles shown here are better for low closure force. They can be friction fit in the groove. They can take up larger gap ranges and tolerances. For instance, I've had many customers use a hollow mushroom D for boxes where you're repetitively opening and closing your box.
Can you tell me a little bit of the difference between a hollow D and a mushroom D?
Sure. Years ago, we had an applications engineer that was designing in a hollow D profile, and the customer had a strip of PSA along the bottom of the D. They noticed that when they were pushing down vertically, that the PSA in the bottom of the hollow D would actually come up and delaminate from its ledge. So the engineer at Comerix created a mushroom D, and the little bump inside actually prevents the bottom of the D from coming up. So it makes it an excellent choice, like I said, for repetitive opening and closing. Good question.
And from what I know about gaskets, these all seem like they're a lot easier to compress compared to the profiles on the last slide, right?
Yes, and we'll get into compression ranges in a couple more slides, but it is very important to realize you can do 100% of the ID, up to 50% of the OD minimum. So these can take up larger gap ranges, as mentioned. And of course, there are many, many custom shapes. So there will be a link to our elastomer catalog, and you can do some light reading and look through all the different profiles that we've made over the years.
The general principle that we typically go with is, if you can imagine it, we can make it. We probably have several thousands of different profiles in different shapes, different dimensions, all that are relatively easy to design or modify based on customer requirements.
Part of this webinar that we really wanted to bring home to you guys was the common mistakes that a lot of people use. You know, there's a lot of different custom profiles that you could choose from. There's, 3 to 4, 5 different types of binders. There's multiple fillers. So Ben, have you ever heard of an instance when someone chose the wrong filler or the wrong binder?
Yeah, a couple times, and fortunately, it came out in testing that it wasn't necessarily the best fit, and we were able to take care of it early on. But it's really important to understand the requirements that you have going into an EMI shielding application. So if you've got flow down requirements from an EMI shielding specification, or understanding the environment that the end product is going to be in, is pretty important when we get to this part of the design process. One of the other things is that you really shouldn't ever have to sacrifice profile qualities in terms of an outside diameter, an inside diameter, a specific dimension, because there is so much design flexibility in the proper gasket.
And another thing too, with regards to the choosing the wrong filler or the binder, you don't want to pick a pure silver gasket when you only need 30 dB of shielding. A nickel graphite might suffice. And so it's really important not to specify a Mercedes if you're only trying to buy a Chevy. In this next section, we're going to talk about overmolded and vulcanized covers. And that means that we take the metal substrate or the plastic substrate, and we actually compression mold this material onto the gasket. It's not glued on, it's molded to, so it's a very robust solution. Something that can be easily opened or closed if needed.
Sierra, I recognize that this section is titled Overmolded or Vulcanized Covers. Can you talk to why they're specifically covers?
The gasket is going to get molded onto one side of the box or the other, and usually the cover is lighter weight and easier to ship across the country because these need to come back to Comerix to be molded in-house.
Gotcha. What are some of the other benefits of overmolded covers?
Well, like I said, the robustness of being able to open and close and not have the O-ring pop out. I had a customer several years ago and they had designed in a simple spliced O-ring in a groove, and it just kept popping out during installation. They didn't want to spot bond it. They were trying to tape it down. They had to install the cover vertically, so it wasn't horizontal. You'd think that would be a lot easier. So we actually talked to them about designing an overmolded cover. It was more complex than a simple O-ring, but it saved them immeasurable time and money during the manufacturing process, eliminated a lot of frustration. And, one of the things was they were paying the engineers to come in and figure out the problem, and they're a lot more expensive than an assembly worker per se. So there are a lot of benefits, measurable and immeasurable. Another option for either extruded or molded parts, when there's a really extreme environment, like you're on the deck of a Navy ship or you're in a tropical location where there's salt fog, humidity, moisture, it can be a huge problem. By using the non-conductive seal outboard exposed to the environment and the conductive seal inboard exposed, blocking the EMI shielding from inside and, radiated immunity and radiated susceptibility, it just removes the electrolyte, the water, and protects the conductive gasket from exposure. So, electrolytic corrosion is something we'll talk about in a few slides, but it's a big deal. So if you have a very extreme environment and no water should get in, this is a very, very good solution.
And these co-extruded gaskets also come in a number of sizes and shapes, right?
Yes, actually, there's a whole section in our catalog with several profiles that are already tooled up. But if you wanted to design your own, completely doable. However, you just have to realize, not with the extruded, but with the molded, you need to have a transition zone, a peak or a valley in between the materials so that they're not molding into each other. So just keep that in mind.
Good to know. One of the important considerations when it comes to overmolded or vulcanized covers is that they typically do require a slightly longer design cycle and a longer lead time. Long term, that lead time might actually be shorter. Typically, because this is all done at one place, or overmolding is done at one place, it requires fewer subcontractors and less shipping back and forth and less supplier management. But overmolded covers typically do require a little bit more design effort and more engineering support.
Interesting. Good to know. I like to tell my customers that if they can let us be the supply chain lead, we have a lot of local machine shops that can do the work and then just drive it over to Comerix. We mold it and we ship it.
All right. So it looks like our next section, we're going to talk about some of the housing and groove design guidelines.
Great. I'm ready.
As you all can see here, while all of these are very valid and very common groove and housing designs, some of them tend to be better in terms of EMI shielding and environmental sealing. For example, on the left, you see a flat gasket between a cover and a housing. While typically a good environmental seal, it doesn't offer metal-to-metal contact and can therefore pose some design challenges. One of the most common is there in the middle, where you see a gasket designed into a groove. That's that solid O that Sierra talked about. And the benefit is that it provides a metal-to-metal contact. Whereas if at all possible, on the right, you'll see a gasket designed into a groove along with a tortuous path. That tortuous path simply adds to the environmental sealing as well as the EMI interference shielding.
So I guess, Ben, then this would really depend on the amount of shielding, possibly the exposure to water. You might not always have to design a tortuous path. Do you think you should always design a tortuous path?
No, you definitely don't. And That option right there in the middle, like I said, is probably our most common. It lends itself well, especially if you can put in a groove. We realize that a lot of times applications aren't able to do that. So even that example on the left is going to be a great EMI seal, an environmental seal that can last decades if designed well and using proper materials.
It looks like the fair slide, the gasket is actually exposed to the environment.
Yeah, it is. And that's not necessarily a bad thing, especially considering that these conductive elastomers are meant to be an environmental seal.
Good.
One of the important things when considering housing design is also understanding how much force you have to compress some of these gaskets. So for example, cover thickness and bolt spacing are two pretty important factors when considering the type of elastomer, the hardness of the elastomer, and even the size of the housing overall. Sierra, have you had some experiences with this?
I have, yeah, actually. I had a customer that designed a box, and it was probably 6 inches by 6 inches, and they only had one screw in each corner. So there was a lot of leakage going on. But I mentioned to them, I said, okay, look, bolt spacing is to the 4th power over cover thickness to the 3rd. They were trying to use bent sheet metal, and the gaskets are very hard, 65 plus or minus Shore A. So we got them back on track. We reduced the distance between bolts, and we ended up passing the test.
Especially because if you look at this equation, right? Some of the things when it comes to EMI gaskets aren't really controllable. So for example, gasket deflection force, for most profiles or most materials are going to be about the same, but things like bolt spacing or cover thickness might have a little bit more design flexibility depending on how early you are in the process.
Definitely something important to look at in the beginning. A lot of common mistakes made around housing design. So compression forces, I mentioned we'd be talking about this a little while ago. So if you notice, here's the different types of profiles that we were talking about. And if you look at the chart, there's a minimum, a nominal, and a maximum deflection range. And solid O, 10% minimum, 18% max nominal, and 25% max. However, a flat strip, 5% minimum, 10% nominal, 15% of the height. It's really important to design your gasket to be properly compressed. These gaskets are filled with free-floating metal particles. So not having the minimum compression will actually prevent the particles from touching and not give you shielding or grounding that you're looking for. Whereas if you have greater than the recommended compression value, you can actually crush the little particles and reduce the ability for the gasket to spring back after taking a compression set, say in heat or cold environments. It's really important to pay attention to these compression forces.
And Sierra, I guess the deflection ranges don't really matter when it comes to things like the size of the gasket. So for example, if you had a gasket that's a solid O profile that's 70 thousandths versus a solid O profile that's 1/4 of an inch, you're still looking for that same compression range, right?
Correct. Yeah, good question. All right. So there's always a lot of questions around gasket adhesion options. We've talked already about friction fitting a hollow O into a groove. We've briefly touched on spot bonding. A lot of you have dealt with sheet stock with pressure sensitive adhesive. So it's always important to refer to the elastomer handbook for exact groove dimensions to fit existing profiles. We have all of the recommended groove dimensions for hollow or solid O's, mushroom D's, but there are certain situations where you can't friction fit, like in a solid profile. So what you need to do, if you're worried about it popping out, is spot bond it. We like to tell you to use a non-conductive RTV to match the binder system. So if you have a silicone gasket, you're going to want to spot bond it with a silicone RTV. Same with a fluorosilicone gasket, you're going to want to use a fluorosilicone RTV. Ben, do you know why we recommend non-conductive adhesive versus using a conductive adhesive?
Yeah, so typically non-conductive adhesives will actually have a better adhesive strength or lap shear force. A lot of conductive adhesives end up sacrificing some of their force because of the conductive particles. Additionally, the conductive particles conductive adhesive can add to the galvanic mismatch between the substrate or the frame, the gasket, and the adhesive itself, which just adds more to the equation and typically complicates the process. Sierra, one of the options on here is rivets or bolts. Can you describe how that would work with some of our gaskets?
So, for instance, we looked at a hollow P design, which is like a hollow D, but with a leg coming out. Sometimes you need to mechanically fasten your gasket. PSA may not be robust enough. It could be a very critical application where it has to adhere, and rivets can be very helpful. Also, compression stops can be needed in cases where you're afraid that someone could over torque the gasket. So we all make fun of the 18-year-old kid on the deck of a Navy ship. He's the one that you design for because you're trying to make it foolproof. So if you are worried about things like over compression of your gasket, compression stops. If you're worried about the gasket falling off, you can rivet it on. But yeah, good question. Let's talk a little bit about groove basics. It's a pretty quick slide. We like to use straight rectangular grooves for elastomers. Tongue and grooves can be used with caution. We should try to contact applications, make sure that we've got the right profile if that's what you're stuck with at the time. Dovetails are a no-go. We do not like dovetails. And we'll talk about that as why, but don't use dovetails.
So what you're saying is that we should absolutely never, ever use dovetails if you can get away with it.
Correct. And we'll talk about why in the common mistakes section at the end. Another important thing you have to really consider when designing your housing and your groove is the bend radius. So say you have a hollow O and you design a 90-degree corner, that hollow O is going to pinch. And what happens, Ben, when you pinch a gasket in a groove?
Yeah, I mean, if you pinch the gasket in the groove, you're really no longer maintaining that original profile that it was extruded as. What that means is you're probably not getting the ideal sealing at that point where it's pinched or bunched up. You're also probably not getting a great electrical contact, which could sacrifice some of your EMI shielding.
So you're saying if we pinch, you can get leak points for water and EMI?
Exactly.
So yes, you want to make sure you have a minimum bend radius, which is in the catalog. So keep that in mind.
One of the types of shapes that we haven't talked about yet is a die cut gasket. So with a lot of shapes or a lot of applications, we can take large sheets of material and die cut standard or not standard shapes out of that. That could be rectangular. It could be all kinds of custom designs based on how the gasket needs to interface with a particular housing. Some of the key tips when it comes to die cutting is actually making sure that you take into consideration the wall thickness to the gasket ratio thickness. Here's a great example of what it looks like when you design a gasket that's too large for a groove. So what you see here are pinch points and potential damage to the gasket, while at the same time significantly increasing any kind of compression force needed to compress this gasket. This animation shows a gasket that's actually too small or undersized for the groove. What you're getting here is less than 10% deflection or almost no deflection at all. So you're really not getting any kind of electrical contact at this groove, while at the same time getting effectively no environmental sealing. Finally, we've got the Goldilocks gasket. So it's a gasket that's designed properly for the groove to make sure that there's no overfill of the groove, so the gasket isn't being damaged, while at the same time compressing the gasket the proper deflection range, in this case for a solid O, between 10 and 25%. Sierra, I know you wanted to touch on some of the common mistakes when it came to housing and groove design.
Yes, there are some very important ones. The one we've been alluding to is not using a dovetail. And the reason why is conductive elastomer gaskets should always be designed in compression. We don't want to design in shear or tension or rotation of any kind because of FOD concerns. So you can install a gasket into a dovetail groove. It could shear on the way out. If you're trying to take it out, it could shear on the way in. The other point is that elastomer gaskets need a minimum of 3 points of contact to create a ground or a shield. If you have a gasket that is underfill in a dovetail groove, it could give you as little as only 1 point of compression, which is not going to give you shielding or grounding or water sealing for that matter. Another common mistake is trying to apply grease to the gasket. The point of grease is to reduce friction, and you're not using this in friction. So it's one common mistake. But the other more important, less recognized, is the fact that if you put too much, it could cause a dielectric barrier between your housing and your gasket. Ben, have you ever seen anyone try to use conductive grease before?
It's honestly becoming less and less common in applications to use conductive greases. Typically, they aren't really needed, and it touches back to one of our points earlier about adding additional materials that may create galvanic mismatch between the substrate, the gasket, and the grease itself.
Good point. And then the other common mistake is applying too much adhesive when you're spot bonding. We talked about using a non-conductive adhesive. Ben spoke to that. It's because it's a thinner. You can put a tiny drop, and it's not electrically conductive. So trying to use a conductive adhesive is thick. It can cause bumps in your fill, and your gap won't be perfectly flat. And it's really just trying to hold it into place.
Sierra, a lot of the common differences or common mistakes in this section are basically treating a conductive gasket like a non-conductive gasket. So, for example, I know a lot of non-conductive gaskets actually require or look for a dovetail groove or need some kind of grease. And in this case, conductive elastomers are just about the opposite.
I really recommend just designing your box to house an EMI gasket from the beginning. Assume that you're going to have EMI issues, because it's way more difficult to take a non-conductive gasket and then design in a conductive gasket due to the compression forces, the groove sizes, underfill. Maybe you designed a dovetail groove and now you need an EMI gasket and you have to change your whole groove design. So I think it's important to just harden the system for EMI. And then when you go through your testing and you don't need it, it's easier to put a non-conductive in there. It's a cost down, and you're the hero.
In our last section before the Q&A, we're going to touch on some of the corrosion and environmental factors that need to be considered for EMI gaskets.
There are two types of corrosion. We have galvanic, which is caused by two dissimilar metals corroding. And there's electrolytic, which is caused by oxygen or water, say rust.
And it looks like some of the different conductive fillers are actually better for minimizing that galvanic corrosion, right?
Absolutely. So there are very low-cost materials that are for industrial applications, like a nickel graphite or a carbon, something that's not as corrosion resistant, but good enough to do EMI shielding. And then you've got your high-octane materials, like your nickel aluminum material or your passivated silver aluminum, which are very galvanically compatible with housing materials like stainless steel or aluminum.
One of the other ways to minimize galvanic corrosion would be to attempt to eliminate that electrolyte. So things like salt fog. If you're not directly exposing it to the conductive elastomer gasket, then you shouldn't have much galvanic mismatch.
Good point. That's actually where possibly the co-extrusion might come in, where half of it's conductive and half of it's not. That might be a good opportunity. So Ben, what are some common mistakes?
Yeah, so when it comes to the housings, not only is designing a proper housing a big deal, but the housing material also starts to have an impact. For example, we would almost never recommend magnesium housings, partially because they don't stand up well to corrosion, as well as, most environmental factors, as well as galvanic corrosion against just about any EMI seal. One of the other things that's important to note is EMI gaskets and conductive elastomers need to mate up against a conductive surface. What that means is a untreated or a chem-filmed aluminum, for example, whereas anodizing a housing substrate will actually do the opposite and create a non-conductive bond between the gasket and the housing.
All right, everyone. We've gone through a lot as far as housing design, corrosion concerns. I feel like the top 3 EMI seal design takeaways today were, look at your performance requirements. What does your customer need as far as shielding effectiveness goes? What about aging requirements, application requirements like temperature and humidity, mechanical constraints? What's your cover thickness? What kind of real estate do you have for a groove? Are you able to get a good bend radius around a corner? And then environmental considerations. Is this going to be indoor? Is this going to be in an outdoor? Is this going to be on the deck of a Navy ship in a very corrosive environment? So there's a lot of things to consider. And with that, I will thank you guys all for your participation, and we will unmute ourselves and ask if there's any questions.
All right. Hello, everyone. Hope you enjoyed that quick half-hour overview of EMI elastomer gasket design. At this point, we're going to take some of the questions that we've been getting. So if you do have questions while we're answering some of these, please feel free to use the Q&A option. Type your question, and we should be able to get to just about all of them that we have here. So Sierra, if you want to start with the first question.
Sure. One of the questions, excuse me, that I did see a few times was, will this be available afterwards? And yes, Jared is going to be putting this either on the website or sending a link out. I'm not exactly sure how we're going to get it to you, but we will be doing that. Let's see,
One of the other questions that we've been getting has been about the design flexibility of the various profiles. So if you look through our conductive elastomer handbook, we probably have several thousand profiles listed there, from hollow O, solid O, P profiles, as well as some custom profiles that we have listed. In addition to that, we probably have thousands of other profiles that we've made, just haven't listed in our catalog. When it comes to new profiles, the question was whether there's an NRE that's associated with it. Typically for extruder profiles, it's a relatively small NRE, somewhere in the range of $400 to $500 for the extrusion die.
Okay, I see a question here from Darren. Do conductive O-rings have a shelf life after they are vulcanized? Conductive elastomers without PSA, without adhesive, have an indefinite shelf life. Good question.
One of the other questions we got was about overmolded covers for radial seals. Radial seals typically provide a slightly tougher engineering challenge for EMI elastomer gaskets. With those, we prefer to kind of take it on an application by application basis. So please feel free to reach out to either Sierra or myself, and we'd be happy to talk to you about those.
I see one from Mark, and he says he may have missed it. Is there a bolt spacing recommendation? Yes, there is an equation in the catalog. It's a lengthy one, but as mentioned, it's the cover thickness versus bolt spacing is very important. So yes, it is in the presentation as well as in our catalog.
One of the other questions that came in was about EMI shielding of various profiles. Typically, we notice that the EMI shielding is actually driven by the material itself rather than the specific profile. So, for example, a hollow O gasket can give you the same, if not better, EMI shielding compared to a solid O profile. It just depends on the proper housing design, groove design, gasket design, as well as material choice for what you're looking for.
Let's see, from Nandu. Are there any concerns with using a fluorosilicone gasket with a metallized plastic cover? Different types. This presentation is focused on metal covers, but I'm curious to see if there are particular design points to pay attention to when using your gasket with plastic covers. The most important thing to do is to galvanically match the conductive coating to the conductive gasket. When designing a conductive coating onto plastic, those two materials also have to be compatible. If you're using say a chemically resistant plastic, paint is probably going to wipe or drip off and not adhere to the substrate very well. But you do want to make sure that the conductive paint on your plastic is in contact with the conductive gasket. That's the most important thing. And to match the conductive particles so you don't create galvanic cells. Hopefully that was...
The next question is about groove dimensions for D profiles, both hollow and solid D profiles. While they aren't necessarily published in our catalog, we're able to provide those recommendations. Feel free to reach out to either Sierra, myself, or our applications team. The reason we don't publish them is because D gaskets tend to compress slightly differently than solid or hollow O profiles. Which is why we look for slightly different properties in those group dimensions.
I have a question from Roland. What about form-in-place gaskets? I want to know if you guys are using that type of gasket. We didn't specifically go into form-in-place gaskets today. That could be something that we can do in the future. I would say if you could write down Ben or my contact info and get in touch with us, and we can have a off presentation discussion about the form-in-place gaskets.
We have a question from Ken about recapping the rationale for avoiding dovetail grooves. Typically, we notice that dovetail grooves end up doing damage to some of the conductive elastomers. They can cut into the gaskets, and especially with smaller profiles, it's a little bit tougher to make sure that you aren't damaging the profile with the groove itself. Additionally, dovetail grooves can pose an issue in terms of the electrical contact points when the gasket is deflected, based on our recommendations for gasket deflection, as well as groove fill.
Okay, I have a question from Dominic. Is the bolt spacing applicable to all seals or just EMI applications? So bolt spacing is important for if you don't want water intrusion in a non-conductive application, but it's very important for EMI. So I would say yes, it is applicable to both. But for EMI, it's really about water and radiated susceptibility and radiated immunity.
Another question we have is about fungal resistance. We do have testing on just about all of our profiles and our materials in terms of the various binder systems, as well as the various filler systems on fungal resistance. So please feel free to reach out to either of us if you're looking for specific data or specific reports that we've run. We'd be happy to share those.
Okay, I have a question from Ken. Unfortunately, he missed the rationale for avoiding the dovetail groove design. I'm going to recap that for you, Ken. Dovetails, so EMI gaskets are meant to be designed into compression. And when you have a dovetail groove, trying to install the gasket or remove the gasket, it could shear. Also, you need minimum of 3 points of contact to give yourself grounding and shielding. And inside a dovetail groove, if you are underfilling, if the gasket is too small, the lid will not come down. It won't touch the gasket. You may only have 1 point of contact. So for FOD concerns and also shielding concerns, it's very important to avoid dovetails.
A question from Will regarding the difference between conductive versus non-conductive adhesive choices. So typically for a lot of our applications and spot bonding gaskets, either into grooves or along a flange, we actually recommend a non-conductive adhesive. The big reasons for that are that non-conductive adhesives typically have a better adhesive strength or a lap shear force. Additionally, conductive adhesives tend to be thicker, and the addition of the metal fillers in that conductive adhesive adds to the potential for a galvanic mismatch or the difference in galvanic potential between the substrate, the conductive elastomer, or the conductive particles in the elastomer, as well as the adhesive.
I have a question from Rohit. Which one gasket is used most commonly in marine or naval applications? So in naval applications, you want a very galvanically corrosion resistant gasket. So our nickel plated aluminum is the most galvanically resistant from corrosion gasket that we have on the market. Silver aluminum is also a material that has been used in many, many applications. Depending on the severity, I would say either the nickel aluminum or the silver aluminum would be my first choice.
A question from Alejandro about where you can find our EMI handbook. If you go to our website, parker.com/Comerix, you should be able to get to the EMI handbook through some of the quick resource guides or following the links to some of the elastomer gaskets under our literature. You should be able to find it there.
All right, a question from JB. What are some emerging trends you see in EMI RF shielding? I'll answer this, and Ben, if you have anything to add to it. One thing is that, for years we've been making these materials and we have test data up to say 18 gigahertz. We are now seeing higher shielding requirements. There are Boeing aircraft currently flying that were tested to 96 gigahertz. And so I think that the requirements for shielding are higher, like 5G and things like that. So I'm just seeing higher requirements, in the 90s, instead of just 20 dB of shielding, 30 dB, we're going up into the 80s now.
Yeah, and to build off of that, Sierra, I completely agree. Years ago, or if you look back through old requirements on EMI shielding frequency ranges, typically they would end at about 18 gigahertz. Now, as Sierra mentioned, they're going up to plane wave frequencies in the 40 gigahertz range, as well as even higher than that for some specific defense and aerospace applications. One of the questions we have from Paul is about using super glue drops to bond O-rings to aluminum housings. Typically, we don't recommend using cyanoacrylates or really any super glues. The problem with that is that typically they don't have a great adhesive force on our silicone or fluorosilicone gaskets. Additionally, when super glue hardens, it ends up hardening to a point that's far stiffer and far harder than the actual elastomer material. What that does is it creates a bump, or it creates a point of either no electrical contact or no physical contact between the gasket and the substrate, which can lead to issues if you're doing things like long-term testing or have to have that gasket in an environment for a longer period of time.
Okay, I've got a question from Will. For a custom extrusion, is it important for all the walls to be uniform thickness? So think about, when you're a kid and you throw you have your, what the heck are those called? Like, let's say it's a spaghetti machine, right? And it's coming out, extruding out at a certain speed. It needs to be uniform because there's issues with curling and, the speed at which it comes out. So I would say, yes, it has to be a uniform thickness.
We have a question from Jeff about the relationship between a conductive elastomer's DC resistivity and its shielding effectiveness. That's actually a great question and an important nuance. While there's some gaskets that we've developed, or some materials, I should say, for example, our nickel-plated aluminum that provide the highest shielding effectiveness at various frequency ranges, they actually have a relatively high resistance, or DC resistivity, which means a lot of the times they won't meet low contact resistance requirements. The reasons for that are that various conductive fillers end up having different particle morphologies that can lend themselves better to EMI shielding, but not contact resistance. So for example, a silver-plated aluminum particle is going to have a much lower resistance or resistivity than a nickel-plated aluminum because of the inherent conductivity of silver versus nickel.
Okay, John had a question. Do the same principles apply to a form-in-place gasket materials? Yes, as far as galvanic compatibility. The dispensing is gravity fed, it's different. And we can definitely take that offline and give you more details on that, John. It wasn't something we covered today.
We have a question from Will about a custom extrusion in terms of wall thickness being uniform. There's a lot of, again, going back to the design flexibility, there's a lot we can do with various wall thicknesses and various parts of gaskets at different thicknesses. It's very much so application specific, where you're seeing compression force, what kind of compression forces you're able to provide, how much outward resistance the gasket needs to provide from an environmental sealing application. So I'd say in this case, feel free to reach out to one of us and we'd be happy to talk through the specifics there.
Okay, question from Richard. Do you occasionally waive the tooling of a new profile so that you can offer it to other customers? Every product, every gasket is specifically made to a customer print. That is their proprietary information. We do not sell that to other customers. We have a lot of off-the-shelf materials. However, think of a hollow profile. There's a specific wall thickness. There's a specific ID and OD, outer diameter, inner diameter. We can switch the mandrels out to make different profiles where we wouldn't charge you for tooling. But specifically, if it is to a customer part or a design, then that would stay proprietary and would not be offered to other customers. But yes, we can waive tooling for different scenarios.
One of the questions we have is about different complicated gasket cross sections and whether they're with more contact points and whether they provide a better moisture seal than simpler ones. That's actually not necessarily the case. For example, if you're able to design it in a flat gasket that you're able to put a lot of compression force on to compress to our nominal recommended 10%, is going to give you a fantastic environmental seal. At the same time, a well-designed hollow O profile in a groove is going to meet even the highest submergence requirements. So whether that's IP 65, 66, 67, or other NEMA requirements, we've seen hollow O profiles in gaskets used in long-term submergence as well as driving rain applications with no issue about any kind of environmental leakage.
Okay, I've got a question from Tim regarding for lower closure force. Okay, I'll just read it. From page 18 of the Conductive Elastomer Engineering Handbook, for lower closure force and even more gasket deflection range, consider a hollow profile. However, these may not provide weather sealing under challenging conditions. And so what are some of those challenging conditions where you should not use a hollow seal with water? So think of say a NEMA 4 or an IP67 rating where your box is going to go underwater 1 meter for 30 minutes. The pressure of the water can actually collapse a hollow profile wall depending on how thin it is. So we like to use solid in water applications. It's not always the case, but water pressure can actually build up and collapse the walls, and you can get leak points. So that's probably, I think that's what you mean.
One of the other questions we have is about how to match different housing materials with different gasket materials. In our Conductive Elastomer Handbook, we talk about, we have a section on corrosion resistance and which materials will mate up best against various housing materials. So typically, our most common we see is a conversion coated aluminum substrate, but by all means, we've seen customers have housings that are stainless steel based, all kinds of various metal or metallized plastics that can mate up pretty well against any of our various gaskets. So again, feel free to reach out to us. It's kind of a more application specific question.
I have a question from Roland. Any gasket recommendations for shear applications? For example, when a design requires both vertical and horizontal contact surfaces. So as we've said a couple times, we don't recommend an elastomer gasket in shear. However, Comerix makes a lot of different kinds of gaskets, that we didn't talk about today. We do have metal gaskets, we have mesh strip gaskets, beryllium copper spring fingers. Metal does better in shear. So I might offer, if you also need a water seal, you may design a dual design with a metal gasket, not a conductive elastomer.
We have a question from Tim about customers splicing their own hollow gaskets or solid gaskets together. By all means, we have seen customers do that. When we splice gaskets in-house, what we do is we use a special splicing compound and cure it under heat and pressure. What that does is it makes sure that the splice actually ends up being one of the toughest points along the gasket, so you aren't seeing any breakage at where the gasket comes together. Again, that being said, we have had customers splice the gaskets in-house themselves. There really isn't a difference in terms of splicing hollow O profiles versus solid O profiles, just as long as you're making sure to mate the two ends well together and make sure that that adhesive is giving you the strength of the bond you're looking for.
I have a question from Brad. How large is the MOQ for custom extrusion? So to build a custom extrusion die is very inexpensive. I'm going to give you a ballpark estimate of around $750 to $1,000, depending on the complexity for a custom extrusion die. So not very expensive.
A question from Paul. What is the shelf life for PSA for a silicone-based elastomer? Traditionally, the pressure-sensitive adhesive is the driving factor for the shelf life of our gaskets. So the PSA shelf life is actually 12 months. So if you were to receive a gasket that didn't come with a PSA, it would have a effectively indefinite shelf life, whereas with the PSA it would be 12 months.
Okay, I've got a question from Will. Do you rate your gaskets for IP, and would you certify to say that IP67 is a rating? So that it's a difficult test to pass. It's not something that you can't. We've done it before. There's some design considerations. We thought about putting them in this presentation, but we can go over this. So you're going to want to use the bigger the gasket, the better. You're going to want to use a solid profile. You're going to want to have an elastomer with smooth surface. There's a lot of considerations. You're going to want good bolt spacing. You're going to want a good thick cover. So it has been done before. Some customers choose to use a dual gasket solution. It's not necessarily the gasket that's rated, it's your design of how you design. So hopefully that answers your question well.
One of the questions we have from Brian is how popular is a mushroom D shape versus a hollow O, P, and D? It really is very much dependent on applications. Mushroom D gaskets are relatively popular in large gaps. They're used, I would say, a lot in applications where there's a large stack up of machining tolerances or assembly tolerances. Hollow O's, because they come in so many different sizes from down to about 60 thousandths, all the way up to quarter of an inch and even larger. There's a lot of flexibility across the board, and it just depends on what the specific requirements are. P gaskets tend to be used well where there's no groove and where there's a larger flange, or that need, for example, rivets or bolts to be assembled together.
Okay, I have a question from Hamilton. Can you mold or extrude conductive press-in-place seals? The answer is yes. The extrude press-in-place would be a hollow friction fit in a groove gasket. We also can mold what are called diamond seals, and those have little bumps across the profile that they press in place. So yes, we can. Definitely want to get with us on the design of your groove initially so that we can make sure that that's optimized.
We have a question from JB about how is Parker approaching these increases in frequencies. One of the things that we're constantly doing is running additional EMI tests at various profiles on our conductive elastomers. As we see customers bring in these requirements, we look to see what we can do with regards to adapting them. One of the things that was mentioned at the very beginning of the presentation is that we actually consider ourselves a material science company because we do a lot of the particle development in-house. So for example, that nickel-plated aluminum particle is a particle that we developed several years ago and then began to incorporate it into our conductive elastomers. So into a silicone base, into a fluorosilicone base, into a EPDM base, and now have adapted it into various other paints and coatings and gap fillers. So a lot of the R&D and particle development is how we're getting around these enhanced requirements.
Okay, question from Randy. So I've heard in this presentation it's better to design O-ring grooves for EMI, even if you're starting with non-EMI seals. Are there any issues you've seen with using non-EMI seals with EMI designed groove geometry? So let me just clarify. I see a lot of people come after they have successfully designed their box, it seals for water, they go to an EMI test and it fails EMI. And now they're trying to scramble to fit an EMI gasket into the groove they've already designed. So really what I meant to say there is I would like you to begin with your design concept thinking that you're going to need an EMI gasket. Then it will be way easier when you finish your EMI test and you've passed and you don't need that gasket to put a non-conductive gasket in that same groove. It should be totally fine. But I like to harden it first because it's so much harder to go back and do the opposite. It's basically just setting yourself up and doing it right from the beginning. Hopefully that answers your question. Making your life easier.
Another question we have from Ken is recommendations for specific elastomer material used to seal between atmosphere at high vacuum regions containing xenon. One of the things that we should note is that our conductive elastomers, while they provide a great environmental seal, are not designed to provide a hermetic seal. So things like long-term vacuum or an air seal aren't exactly what EMI gaskets are meant to do. So in this application, I would, again, recommend reaching out to one of us. The best way to think about our gaskets is various binders will have different levels of water vapor translation across them. And again, that depends on how much pressure you have on various sides and how long you're looking for the gaskets or the seals to provide that environmental barrier.
Okay, we've got just a couple more minutes. Will, you mentioned testing for higher frequencies. Do you have an EMI test chamber in-house? Yes, we do. We have multiple chambers in-house at Comerix in Woburn, Massachusetts. And not only do we test our own materials, but we also offer it as a service to test your box. So if you wanted to come to Comerix with your electronics box, you could have it tested for EMI. We have a lot of various UL testing. So there's definitely multiple test chambers in-house at Comerix. So come on over and check it out when this is all over. And then really quick, Kelly, how is the pandemic affecting your lead times? So, we're deemed critical. Our employees are working, we're shipping product. It really hasn't affected lead times that I've seen. I think just trying to get people comfortable working from home has been the worst that we've had so far. So it's not really affecting our lead times that I've seen at all.
A question from Tom regarding static radial seals. And whether we would suggest using a double O-ring groove with a non-conductive O-ring as well as a conductive O-ring. Again, we've kind of answered a lot of these questions with its application specific, just like this one. But I think it's because there are so many requirements and so many nuances to various seals, and in this case specifically radial seals. We have by all means used non-conductive O-rings and then a conductive O-ring to provide that insurance with regards to an environmental as well as an EMI seal. We've also seen just a single EMI conductive elastomer gasket work as both. It would really depend on what kind of seal you're looking for, maybe what kind of materials or what kind of environment the gaskets need to withstand. Where maybe a slightly more durable non-conductive elastomer would help prevent against some harsher chemicals or bleaches or things like that.
Okay, Tim, follow-up question about the hollow O gasket, common mistakes. Wind-driven rain is high pressure as opposed to immersed with a pressure head or sealing in a hydraulic circuit. How about if the configuration is better, metal to metal scenario shown in the housing design tips and tricks slide? Is it okay for a hollow O with wind-driven rain? Yes, it's all application specific. We like to make sure that we fill the groove properly. We have a sample department, so we send you a hollow O and you put it in your box and you spray the hose at it. So there is a little bit of back and forth sometimes. You want to maybe do some FEA, but it definitely can pass the wind-driven rain. That's not really a difficult one. I think the submersion test is the hardest, but yes.
Another question from Will. Do we have information on material outgassing? We do. Actually, in our conductive elastomer handbook on page 42, you'll actually see a full chart with various materials, as well as the TML and CVCM ratings. Many of our conductive elastomers do pass NASA outgassing and are actually used in a lot of high altitude or vacuum environments, as well as satellite and space-based environments. We also have a separate document that lists all of Parker Comeric's outgassing, NASA outgassing past materials, whether that's EMI gaskets, thermal materials, or some of our conductive compounds as well. So you should be able to find that, and please reach out if you can. We'd be more than happy to send it your way.
And also to add to that, Ben, NASA has an outgassing website, and you can look us up. You can look up Parker Comerics on NASA's website for outgassing, and every single Comerics material will also show up on that website.
A question about our Massachusetts facility. So our headquarters is in Woburn, Massachusetts, about 20 minutes outside of downtown Boston. That's going to be where we develop a majority of our EMI shielding gaskets, as well as our conductive compounds. About half an hour north of there, just at the border between Massachusetts and New Hampshire, we have a facility where we do all the development of our thermal interface materials. And then in upstate New York, we have a facility that is dedicated to our conductive plastics. That's just outside of Rochester, as well as another facility in the Jersey area that helps with secondary manufacturing as well as processing of some of our materials.
Okay, and I think probably final question, what is the approximate price delta of the 6503 versus 1298 material? They're within 5% of each other. They're not, one is not more expensive than the other in reasonable terms. So, but we can definitely get you an official quote if you have a specific gasket that you're looking at. They're pretty similar.
Yeah, so that looks like just about all of the questions that have come in through the Q&A. Again, we'd be more than happy to stay on for about another minute or so. Otherwise, you have our contact information. Please don't hesitate to reach out. We'd be more than happy to either answer the questions ourselves or direct you to people within our team who can help.
Also, this is our first webinar with Comerics. So if anybody has any topics that they'd like to discuss, we would love to hear your feedback. We'd love to hear ideas. And thank you guys so much for coming. This is really great. And please don't forget to fill out the survey.